Thanks, Ella. If I'll just make it really short and sweet. Just now, I think, who was it? Tanmay mentioned about EUICC. This is actually an example of it. I'm not sure if you can see it. It's actually a EUICC in a nano-SIM form factor. So it's a kind of like programmable eSIM, but this is in a physical form factor. So you can use it on any phone that supports a nano SIM. So this is the actual kind of like thing that is so they actually this particular chip is actually removed from an iPhone. They removed the EUICC module from the iPhone and they embed it into a nano SIM form factor, so you can actually program it with an eSIM that you register. So just an example. So that aside, there are kind of like, I think, two main points that I want to talk about. The first one is actually on the security of TEs and how we hear a lot of things about how TEs are like not safe, easily broken, secrets are not trusted, etc., etc., etc. But the thing is, I would actually make the argument that it's the same for anything that we as humans engineer or build or program, which includes the so-called math, like cryptographic primitives that we actually invent. Well, the you might actually have certain guarantees or certain proofs about certain cryptographic primitives that is designed, but ultimately you don't operate on that kind of like abstract level. So there's a level of engineering that is involved where we actually convert that kind of like idea, mathematical objects into actual like code that we use in our day-to-day life that our machines can actually execute on behalf of us. And you'll realize that from like 30 years ago up till now, that this is the main source of exploits actually, like those millions and billions of dollars worth of exploits is actually on bugs that that engineers, developers write into the code. So if we think about it that way, I'm a believer of we don't live in a perfect world. We would strive to make things better. That's why I kind of like I agree with what Sylvan says on like how we should actually think of and identify all the ways how we can make like the kind of like the fundamental, at least the theoretic level of guarantees that we can have as high and as secure as possible. But other than that, we have a set of like standard operating procedures where we can use to help mitigate away a lot of this kind of attacks or vulnerabilities. Like there is going to be bug. In the case of a bug or vulnerability, how can we actually mitigate that? In the case where, let's say, a root key is leaked, or there's a particular vulnerability in some firmware or some cryptographic ciphers that we are using, some implementation, for example, OpenSSL. How do we go about it? We coordinate as a community, and then we identify ways to upgrade, mitigate the issue to kind of like minimize the impact. And really, it's this cat and mouse game that we play with the attacker. Like this has always been the case. In the kind of like cybersecurity community, we have the whole idea of defense in depth, layered approach, Swiss cheese model. Relying your entire security on just one thing, be it like ZK or MPC, is just asking for trouble. It's always better, no matter how theoretically good it is, it's always better to have multiple layers of defense. And that is why there is the kind of like the golden rule in terms of the security community. So that's kind of like the first point I want to address. The second point really is about like what we do at Automata Network, or the main thing that we are focusing on is actually on machine trust, on the whole rule of trust. The idea that like just because I have a hardware rule of trust and therefore it's unreliable or untrustworthy, I think you're kind of like throwing the baby out of the bathwater. It can be exploited, but there is a level of difficulty involved in it, just like I explained. And the thing about it is, once we understand this, there's a lot of very interesting things that we can do with it. it's not just for TEE, it's not just for secure execution, it's not just for verifiable computing. The hardware root of trust actually allows us to do something very important called attestation, or to create this chain of provenance. Like, where is the source of my data? Who generated this data? Is this data generated from a ML model? Is it from a particular sensor on my Sony camera? Or is it generated from my iPhone that I'm using, or an Android phone that I'm using? All this is especially important if you want to derive some sort of like trust relation in the world. And like from that point, kind of like from that angle, that's why we choose to really dive in and focus on the idea of extending this trust. How can we derive this trust? How can we extend this trust? How can we make it such that we can have a attestation network that is owned by everyone, a decentralized attestation mechanism? I think a lot of people actually forgot. Like, they think about attestation as like DCAP or EPID or AMD, kind of like attestation primitives that are designed by manufacturers. But back in the day, like 10 years ago, when I first started doing this, you have to design your own attestation primitive. And this is still possible. We can actually build attestation primitives on top of Intel SGX, on top of Intel TDX, on top of AMD SCV. And this is what we are doing. And I'm like very happy to kind of like talk more, but I'll kind of like end here so that we have more time to go into the more interesting discussion.